So let us wait for a few more minutes and then I think we can start if no one else is coming. Okay, so just a few more minutes and then I will begin. Okay, so I think we can begin. If anyone else is coming, I can admit them later on. Okay, so hello and welcome everyone to today's live session of week 7 on the course Fundamentals of Protein Chemistry, which is being taught by Professor Shagota Dasgupta of IIT Kharagpur. I am Srijan Sen, and today I will be discussing with you the lectures which were taught to you in this week in brief, and then discussing with you a few questions which would help you in solving your assignments and the future exams that come up. Okay, so first I will be discussing with the lecture, and then later in the next half we can go with the some questions. Okay, so I'm sharing my slides with you all. So my screen is visible to you all, right? And my voice is audible enough?
Yes.
Okay, that's good. So I think we can proceed. So in the previous class, where we stopped was there we discussed about enzymes, their classification, and mostly how enzymes actually function and in what manner they decrease the activation energy of a reaction, thereby increasing the rate of the reaction. At the same time, we also heard about the different kinds of enzymes that are present over there, a few examples of that. So that was the part 1 of your enzymes. In today's lecture, where we would be beginning is enzyme kinetics and inhibition. So when we know about the types of enzymes and how enzymes function on a general basis, so we can move on to enzyme kinetics and enzyme inhibition. So what is enzyme kinetics to us? So enzyme kinetics is basically a quantitative measurement of the rates of the enzyme catalyzed reaction. That is, you can say it is the systematic study of factors that affect these rates. So how did this enzyme kinetics began? So it began in 1902 when a scientist named Adrena Brown reported an investigation of the rate of hydrolysis of sucrose as catalyzed by the yeast enzyme invertase. And then what Brown demonstrated was when sucrose concentration is much higher than that of your enzyme which they were using as invertase, the reaction rate became independent of the sucrose concentration. So that was her demonstration, or the demonstration of the scientist. So if you can see over here in my slide that enzymes follow a zero order kinetics when the substrate concentration is high. Now this zero order means that there is no increase in the rate of the reaction when more substrate you are adding. So it has reached a saturation value. So one example of this is sucrose breaking down to glucose and fructose. Now this is your Michaelis-Menten equation that has been derived. So previously this similar kind of an equation was also proposed by Brown, where the overall reaction is composed of two elementary reactions in which your substrate forms a complex with the enzyme, followed by you get your enzyme and the product. So this derivation or this proposal was given by So this particular proposal was given by Brown, and this is termed as the Michaelis-Menten equation as well in the later studies. So first E is your enzyme, then S is your substrate, followed by you have the complex, and then you have the enzyme and the product. Okay, so the rate of the complex formation is equal to your, so you have an equation where your ET is the total concentration of the enzyme, and K4 is considered negligible because once the product is formed, it does not go back again to the enzyme substrate complex, and the rate of breakdown of this particular complex, that is your enzyme substrate, is equal to your K2 into the concentration of the complex plus E3 into concentration of the complex according to this particular equation. So thus for your steady state approximation, so what are these terminologies like steady state approximation, then talking about this equation? I will be speaking about them in details in my later slides. So as of now, for steady state approximation, you have this equation where you have the total enzyme concentration, the complex and the substrate concentration, and the entire of your rate of complex breakdown. Okay, so complex formation equals to a complex breakdown. So this equation is the basis for the final Michaelis-Menten following algebraic rearrangement and substitution of this Km. So what is Km? I would be also talking about this in the later slide. And then the Vmax. Okay, so Km is your Michaelis-Menten constant, the substrate concentration that produces half of the maximal velocity, that is Vmax by 2 is your Michaelis constant. So from where we are getting this Vmax, I would be also speaking when I would be describing in details about that double reciprocal plot or the Michaelis-Menten equation plot. Okay. So as of now, what is Km? It is the substrate concentration that produces, it's a constant, the substrate concentration that produces half of your maximal velocity. Like when V equals to your Vmax by 2, that is at that particular point of your substrate concentration is termed as the Vmax. So what is the meaning of this Vmax and then the significance of this Vmax? So if we see that this Michaelis constant has been determined in commonly used enzymes, so the size of the Km tells about a lot of things. So the value which we get from this Km indicates a lot of things. Mostly the small Km indicates that the enzyme requires only a small amount of substrate to become saturated. So you give only a small amount of substrate and the saturation level is reached faster. Whereas if the Km value is high, then a much more amount of substrate would be required to achieve that maximum velocity. So the substrate with the lowest Km upon which the enzyme acts as a catalyst is assumed to be the enzyme's natural substrate. Okay. Although this is not always true, there would be some exceptional cases as well. And then there is a value of Km like 10 to the power minus 7 molar, which indicates that the substrate has greater affinity for the enzyme than when the value for the Km is 10 to the power minus 5 molar. Like we had studied about Kd, Kd, like the your dissociation constant. Okay. From there we could tell that lower the Kd value, higher is the binding affinity. So like that we have the Km. So lower the Km value, so higher the substrate will have affinity for the enzyme, and than that for where the Km value is of a much higher molarity. So what can we confer from this Km value, or what is the significance of the Km value? So it basically gives us an idea about the enzyme kinetic constant. Also it tells us about the substrate concentration that is required by the enzyme to work efficiently. And then we have seen that the lower Km indicates high affinity towards the enzyme and vice versa. So Km is inversely proportional to your 1 by affinity, or you can tell it's directly proportional to your dissociation. Okay. And then some examples of this is given, like hexokinase, glucokinase. Now from the Km value, it also gives us an indication about whether that particular enzyme can be used as a drug or not. Like if it has very high binding affinity with your body, then that can act as a toxin. However, very low binding might not be good enough for your body to act as a medicine or not. So depending on the value of that Km, you can get an approximate idea whether you can use this enzyme as a drug or not. And then these enzymes are used in immunodiagnostics, like we have heard about ELISA and all. So that requires the Km value of an enzyme. So these are the few significances or different ideas that you can get from the value of the Km. Another important term which we had also heard in the last class is Kcat, or the catalytic constant. So at very high substrate concentration, when the overall velocity of the reaction is Vmax, the rate is determined by the enzyme concentration. But the rate constant observed under these conditions is called the Kcat. So you can call that Vmax equals to your Kcat into total enzyme concentration, or if you cross multiply and do, so Kcat equals to your Vmax by the total enzyme concentration. So this is a very nice equation from where you can get a few numerical problems as well. So what does this Kcat give an information about? So it indicates the maximum number of substrate molecules that can be converted to product in each second by each active site. So let us imagine that there are numerous number of active sites and you are performing a particular reaction for say 100 seconds. So in 1 second, by one active site, how many substrate molecules can be converted to the product? That is what we get an idea from the Kcat value, and that is also we can call as the turnover number. So the catalytic constant measures how fast a given enzyme can catalyze a specific reaction. But we need to keep in mind it is only applicable when it is applicable for a particular second by only one active site. So that is important, per second per active site. Now the unit of the Kcat is basically in second inverse. So for most enzymes, you would be seeing the value to be ranging between this 100 to 1000 second inverse. So that is the value of the catalytic constant, and this is the basic idea of what is catalytic constant and what is the significance of this particular constant. Now when we are assuming a thing to be in equilibrium, so previously we had seen the equation of E plus S moving is in equilibrium with the enzyme substrate complex, which is also in equilibrium with the enzyme and the product. So on the basis of that, we are also assuming that your K minus 1 is greater than K2, where the formation of the product is so much slower than the formation of the ES complex, that we can assume this particular situation to be true. Now, what is the steady state approximation, where we are assuming that the enzyme and the substrate, when they are coming together, we are getting an intermediate state, that is your enzyme and the substrate complex. But at the same time, we are also considering that the complex formation, the rate of the complex formation is very negligible, because how much complex that is forming is entirely getting into the product. So therefore, this is where we are assuming that the transient phase or the intermediate phase, it does not change or is close to negligible. Therefore, the d of complex concentration by es by dt is equal to 0. So on assuming this steady state approximation, we can derive the particular equation of your Michaelis-Menten theorem, or the Michaelis-Menten equation, where the total enzyme concentration is equal to your the previously enzyme concentration and the complex formation. So in these two you have the enzyme, so that is your total enzyme concentration. And when you put these equations into this particular reaction, okay, these equations, so when you are putting one equation into the other, this particular values, and then applying the steady state approximation and getting what you get is this particular equation. And this is a very important equation of Michaelis and Menten theorem. Okay, so previously what we did over here was we put the equation of K1 and K minus 1 and K2. Okay, so your K1 is the forward reaction from enzyme plus substrate to your enzyme complex. K minus 1 is the reverse reaction from enzyme and substrate to the complex formation, and K2 is the only forward reaction that is giving you the product. So from there you can tell that the Km, or the where I showed the Km, so the Michaelis constant, so that value is your K minus 1 plus K2 divided by K1. So this is very important an equation, so we need to keep this equation in mind. Okay, so now when we are applying the steady state approximation, and then we are calculating the value, where we have Vmax equals to your K2 into your total enzyme concentration. Sometimes we call K2 as your catalytic constant as well. And then when we equate this particular equation, what we get is V naught equals to Vmax into substrate concentration divided by Km plus substrate concentration. This is very important an equation whenever we are studying enzyme kinetics, and you can expect more than one question from this particular equation. So keep this equation in mind and try to understand how we are getting this particular equation, because this is very important when you are going on to solve a few questions in your assignments and whenever you are giving an exam. So this is a very important equation. V naught equals to Vmax into substrate concentration divided by your constant plus the substrate concentration. Okay, and this is the graph that you are plotting, where you have the V naught in your y-axis and the substrate concentration in your x-axis. So at that particular point, when your Vmax is just half, at that point your substrate concentration is Km, that I was saying previously. So at just the Km of the substrate concentration, where Vmax equals to half Vmax, half of your Vmax, that is Vmax by 2, at that point is your Km. And you can find the derivation over here as well, why you are getting it. So if you put the value into this, so Vmax by 2 equals to Vmax into S by Km plus S. So Km equals to 2S, and then you get at that where V naught equals to your Vmax by 2, at that point your Km equals to your substrate concentration. So you can find the derivation over here. Okay, Now, this particular constant Km widely varies among different enzymes. So, based on what type of an enzyme we are using and what kinetics these enzymes follow, the Km can be expressed in many ways. Like previously, we saw that Km equals to K minus 1 plus K2 by K1. In this case, you would find a different scenario might be like Ks might be known to you, and then you can derive it, and this is also the derivation from the previous one. So we have another constant that comes up from somewhere, and if the value of that particular thing is known to us, then the calculation becomes much more easy. And when we are also considering that your k minus 1 is greater than your k2. So as your k is decreases, the affinity of the substrate increases, and the km can be a measure for the substrate affinity. Okay, now there are a few factors that affects your enzyme kinetics, mostly your the concentration of the enzyme that you are using, because in the equation you would be seeing that there is a term called um, so this Vmax depends somewhat on the total enzyme concentration. So therefore the enzyme concentration has a meaning, or is an important factor that affects the enzyme kinetics. Then you have other natural factors like the temperature, then the pH. You can use some activators, inhibitors, depending on the product concentration, on the texture of the product, or on the structure of the product, it can vary. Then we have the pH, the substrate concentration, and there are other physical agents. So these are a few factors that you need to keep in mind, and the enzyme kinetics on which it depends on. Okay, so another time I'm repeating, it is the enzyme concentration, the temperature, you have the pH, the substrate concentration, we have the inhibitors, the product concentration, the activators, and finally the physical agents. So the mostly important thing that we would like to focus on is on the substrate concentration and in what manner it actually gets affected. So this Michaelis-Menten plot actually acts like a rectangular hyperbola, where the initial velocity when the little amount of substrate is the initial velocity is the velocity when the little amount of substrate that is added, that is in the primary stage of it. Now here we see that we are observing three phases of the curve. So what happens in the first phase, the substrate concentration is low, and then you are increasing it, and most of the enzyme molecules are free, so they combine with the substrate molecule. Therefore the velocity is proportional to the substrate concentration, and at this state your enzyme reaction follows the first order kinetics. Okay, so in the first phase of your reaction, the enzyme the substrate follows the first order kinetics because the substrate is low, the substrate concentration is low. And then when you're actually increasing the concentration of the substrate, the velocity is not anymore proportional to the substrate concentration. That is, almost half of the enzyme molecules are bound to the substrate. At this stage your enzymatic reaction is showing you a mixed order kinetics. So in the first phase it was first order, and then when half of the enzyme molecules are bound to your substrate, then they are following your mixed order kinetics. Now what happens in the third phase? In the third phase, all the enzyme molecules are actually bound to your substrate. Now you have reached a saturation level and no more substrate can again bind to the enzyme molecule. So the velocity maximum remains unchanged. That is when you have attained that Vmax, or the maximal velocity, because the free enzymes is not available, though the substrate is in excess and the saturation level is reached. At this stage the reaction follows zero order kinetics. So these are the three important phases of that reaction, and from the graph you can tell that which phase of the situation. So if you see over here that in the first phase you are observing first order kinetics, and then when it is half bound, that is your mixed kinetics, and then it starts attaining the zero order kinetics in this direction. Okay, so these are the three phases of your of the curve. And this is another plot. Now this is known as the double reciprocal plot, where you are just modulating the equation in some manner or the other. That is, we studied v naught equals to v max into substrate concentration divided by km plus substrate concentration, and if we are reversing the equation in some manner or the other, we are getting a straight line plot. That is what we call as the double reciprocal plot. Okay, so now when we are plotting 1 by v naught in the y-axis versus your 1 by substrate concentration in the x-axis, what we are getting is 1 by v naught, v max is your intercept. Okay, is your intercept, and from the slope you can get the value of km by v max, and ultimately this is your another intercept that you are getting. So we are getting two intercepts, one is the y-intercept and one is the x-intercept, and from there you can get the values of this equation. So this is another important equation which we would be using when we are trying to actually understand when we would be trying to understand the enzyme inhibition mechanism. Okay, so as of now, so from where we are getting this equation, I guess it is very clear. So from the Michaelis-Menten equation, where just why do we call it double reciprocal? Because we are actually reciprocating the entire equation and then framing equation in a manner such that we can get a straight line, and from there what information we can get? We can get the km value from the x-intercept, we can get the vmax value from the y-intercept, and finally we can get the km by vmax value from the slope. Or if we find the slope, we can find either of these equations. And your substrate concentration is your 0.5 km. So that is different when your half of the enzyme is bound to your substrate. At that point we call it the km. Okay. Okay. So this is also called the Lineweaver-Burks plot, where you have the slope as k divided by vmax, where 1 by v naught intercept is equal to your 1 by vmax, and then extrapolated to get the x-intercept, that is equal to your minus 1 by km. So this is when it is not actually affected by any kind of inhibitor and all. So when no inhibitor is present over there, at that point your x-intercept and your y-intercept is this. But when you get and say when there is the presence of an inhibitor, the entire scenario just changes. So now the kcat value for this particular equation would be kcat equals to Vmax by total enzyme concentration, is how many reactions an enzyme can catalyze per second. That is the turnover number. So I have spoken about this previously, and I guess that is clear to all of you. Now for Michaelis-Menten kinetics, K2 is equal to your Kcat, that you can understand from the equation as well. And now V naught equals to your K2 by Km, total enzyme concentration into substrate concentration, that is equal to your Kcat by Km into enzyme concentration into your substrate concentration. Now why are we considering total enzyme concentration to be our original enzyme concentration? Because when the substrate concentration is very less than the Km value, so very little complex is being formed, and therefore the total that we are taking initially is equal to our what is left behind. So that is, the decrease is very less, so we can think or assume that to be more or less similar. So from there we can get this particular equation, and from there we can tell that Kcat by Km is the measure of the catalytic efficiency. So if someone asks us that what is the catalytic efficiency and gives us the 4 options, so then we can tell that catalytic efficiency is Kcat by Km. So that is the entire understanding about the efficiency of a catalyst, or the efficiency of an enzyme, or we can call the catalytic efficiency. Now till this much we had studied where there was nothing that was affecting a particular reaction. but this is the best scenario that we have seen. Mostly what we observe is that there are a few inhibitors that actually stop the enzyme from causing any kind of reaction, or it is inhibiting the process or stopping the enzyme from acting in its own particular manner. So how many types of inhibitions are possible? So there are three types basically: your competitive inhibitors, you have the mixed inhibitors, and the uncompetitive inhibitors. So this is just an example of a competitive inhibitor that is given, where you have a succinate and you have succinate dehydrogenate, where you get the fumarate, and then you have the malonate and you have the succinate dehydrogenase, but no reaction is occurring because where the inhibitor competes with the substrate. Okay, now what is happening in the competitive inhibition? So you have the enzyme and the substrate. So the substrate and the inhibitor both are actually competing for a particular position in the active site of the enzyme, and then in the best scenario what we see is that you are getting the complex formation, and then the product is what you want at the end of the day. But when there is an inhibitor, so there you have got another constant, that is Ki, and that is forming an enzyme inhibitor complex with your substrate as well. And then when this complex is getting formed, there is no place for the substrate to go and bind to the active site, and therefore you are actually observing no reaction. So what is happening? So this is a different reaction you can go through. This is a type of a competitive inhibitor reaction that you would be seeing. Okay, and then you have the Ki value, which is equal to your enzyme concentration into your inhibitor concentration divided by your enzyme inhibitor complex. So your V naught just changes a bit and it becomes Vmax by S naught. The numerator remains the same, but where you see and change is your alpha. So is your Km value, where it increases by a term called alpha. So it becomes alpha Km plus your substrate concentration. So what is alpha? It is given over here, that alpha equals to 1 plus your inhibitor concentration divided by your Ki. Okay, so that is what you get over here. So if you see from the first equation, you have Ki, so Ei by E comes over here, so that is ultimately your alpha minus 1 value. So alpha minus 1 equals to I by, and then from there you can actually get from where you are getting that alpha. So ultimately what equation we want to look over here is this particular equation, where V naught equals to your Vmax into substrate concentration divided by alpha Km plus substrate concentration, where your alpha equals to 1 plus inhibitor concentration divided by the constant that is actually affecting the rate of the formation of your enzyme and the inhibitor. And now when we go on to plot this particular Michaelis-Menten, put this value in the plot, what we get over here, where we have the V naught in the y-axis and the substrate concentration in the x-axis, then what you would be seeing, as the value of alpha increases, you would be seeing the graph to become a bit linear. That is, over here there is increasing. So in this phase you are increasing the inhibitor concentration, and what happens with the increasing inhibitor concentration, your alpha value is also increasing, and with the value alpha value increasing, you would be seeing the graph to be a lot more of a straight line rather than a rectangular hyperbola. Okay, so you would be seeing a difference in the graph. So in the first place there was no inhibitor, so alpha was equal to your 1, and then with the increasing alpha value the graph shows a drastic change. Okay, now when you are plotting that same particular equation in your Lineweaver-Burke's plot or the double reciprocal plot, you can see from here clearly that with the increasing concentration of your inhibitor, the alpha value is also increasing, and with that you would be seeing that the your 1 by Vmax remains the same, but your mine your Km alpha Km value, or your 1 by alpha Km value is increasing. Okay, so from shows an increase, because it is a negative sign, so it was in the first stage and then it is increasing and coming close to 0. So that is the reason, you would be seeing a change in the Km value as well. Now, this was about your competitive. Now coming to the uncompetitive inhibition. So what happens over here? So the the substrate comes and binds to your enzyme, and your enzyme substrate is formed. Now the inhibitor has a very bad habit of going and binding to the complex, and then it does not allow the product formation. So it is actually affecting the reaction in the second step. The first step is happening as it is, but the inhibitor is going and binding to the complex formation, and ultimately you do not get a reaction, but the first step happens as it is, and the effect that you can observe, if you can extract anything from the second step and perform any kind of reaction, you would be observing, but the first reaction is occurring as it is. So over here you see that both the Vmax as well as your Km value is showing a drastic change. So as you are increasing the concentration of the inhibitor, your alpha value is also changing, as well as your alpha max value is alpha dash value is also changing. Okay, so you would be seeing that the Vmax value is showing a decrease, and your Km value is showing an increase, okay, with the increasing I concentration. So this is the graph, the Lineweaver-Burks plot for an uncompetitive reaction or non-competitive inhibition of a particular enzyme. And but however the slope remains the same, because you have in the you have an alpha dash in the numerator and you have an alpha dash over here as well. So after all they cancel out and the slope remains the same, but the values at different concentration of your enzyme, concentration of your inhibitor, you would be getting a straight line but with a different value. The slope remains the same, but your Vmax and Km changes. Now coming to the last type of an inhibition, that is your mixed inhibition, where you see that this particular inhibitor can either go and bind to your enzyme in the first step and inhibiting the first step of the reaction, or also it can bind to the complex, thereby it is also preventing the formation of the product. So in both the cases the product won't be formed, but in which stage it is going and binding, that becomes a matter of concern, and in both the cases you would not be getting any product, so there won't be any reaction. So what do we observe over here is that your Km value shows a change, and it becomes much more complex over here. So it shifts, and you would be seeing the meeting point of all of these three plots. So what do we have over here? So when there is no inhibitor, your alpha equals to alpha dash, which is equals to your 1, and then in the next stage your alpha becomes 1.5 and your alpha dash equals to your 1.25, and here your alpha equals to 2 and alpha dash equals to 1.5. So you would be seeing that with the increasing concentration of your I, you would be seeing an increase in the Km value and a decrease in the Vmax value. So also you would be observing a change in these particular values, and the slope also changes over here. That is your alpha Km by Vmax. So what is your alpha over here? Your alpha equals to inhibitor concentration divided by Ki, that is for your first step, and your alpha dash equals to your 1 plus inhibitor concentration divided by your Ki dash, that is for your second reaction, or that you observe for the complex. So now when we move on, so mixed inhibition is when the inhibitor binds to the enzyme at a location distinct from the substrate binding site. So where the substrate is going and binding, it is not, the inhibitor is not binding, but it is binding to the site where from a different from that of the active site, but what it is doing is it is inhibiting the reaction. So the binding of the inhibitor will either alter the Km or Vmax or both of it. Now your Ki equals to your enzyme concentration into your inhibitor concentration divided by Ei, whereas your Ki dash equals to your enzyme substrate complex into your into your inhibitor concentration divided by your enzyme substrate inhibitor complex. And then your entire equation becomes a bit more complex, where your Michaelis-Menten equation is V naught equals to your Vmax into substrate concentration divided by your alpha Km plus your alpha dash into substrate concentration, where your alpha dash value and your alpha value is known to you. So this is the ultimate thing that you get out of the inhibition study of an enzyme. So summarizing the types of inhibition, so when there is no inhibition, your Vmax remains Vmax and your Km remains Km. Now when there is a competitive inhibition, your Vmax remains the same, but your Km value increases. Now, when there is an uncompetitive inhibition, your Vmax value is decreased by alpha dash, and same is observed for Km, which is also decreased by alpha dash. And in the case of mixed inhibition also, you see the same scenario, but here something is wrong given over here. So it's Vmax by, just a minute. Yes, so it's Vmax by alpha, and this becomes your alpha Km by, okay, no, uh, sorry. So yes, so for the mixed inhibition, what you see over here is Vmax by alpha into, so Vmax by alpha dash, that is, it is decreased by the alpha dash value, and your Km shows alpha Km by alpha dash. So depending on whether alpha is more than alpha dash or alpha dash is more than your alpha value, so depending on that you can tell whether your Km value is increasing or decreasing. So this is very important, and you need to keep in mind in which cases your Vmax is changing and in which case your Km is changing or remaining the same. So this is entire of your enzyme kinetics and the enzyme inhibition mechanism that you mostly observe for an enzyme, and that. Okay, now we would be jumping on to solving a few problems. So as I do it, so you people would be solving it, and then I would be discussing with you the answers. Okay, so you can answer me in the chat box. Let us see. Okay, so the first question. The first question says enzyme velocity can diminish over time due to decrease in substrate concentration, product inhibition, pH changes, thermal inactivation. So everyone, if you should be answering this, that will actually help you in solving most of your assignments and all, and it feels good when you people are interacting. Okay, so try answering them. Never mind if it's wrong or uh, you have thought it in the wrong manner, but try answering them. Okay, I've got an answer. Others, please. So what are the factors that actually affects this enzyme velocity? So I have got an answer C, I have got D. So let us see. So decrease in substrate concentration. So we have seen that when we are decreasing the substrate concentration, actually your enzyme is dependent on what factors. If we go back to that slide, we can get the answer. So the substrate concentration is very important a factor for that. So we one is correct. Product inhibition. Okay, so product inhibition is also correct because inhibitor playing a role in any of the state, say during binding to your with your substrate or with the complex or with the product, like your product is not formed, that will also be affecting. Okay, next the pH, that is also an important factor over there because your hydrogen concentration does matter in some enzyme kinetic reactions. And lastly, a thermal inactivation, that is your temperature, that is also an important factor. So ultimately all of the four options are correct over here, so option C is the right answer. So 1 2 3 4 all would be correct. Okay, the next question. Let us see. So the next question says this reaction represents the, okay, so we have a particular reaction and we have the constants. Formation of an enzyme substrate complex followed by the breakdown and release of the product. Now the rate of ES breakdown will be, okay, so yes, let us see what will be this one. Right. So what will be the rate of the ES breakdown? Try finding out the answer. So we have K1, K minus 1, K2 and K minus 2 over here. And the question is, if we simplify the question, the rate of ES breakdown. So what is going to be the rate? So I'm just giving a hint. In those cases from where your enzyme substrate is actually breaking or getting back or getting to the product, that is going to be your rate for the ES breakdown, because here it is not talking about the ES formation or the ES breakdown in total, but it is talking about the breakdown process. Okay, I have got an answer. Okay, anyone else who would like to answer or try? Okay, good. I have got another answer. So let us see what is the equation telling us. So our main focus is ES, that is the complex. So breaking down means either ES is forming the product or getting back to the substrate. So which constants are actually affecting it? So when it is getting to the product, we have the forward reaction that is being controlled by K2, and the backward reaction that is being for substrate formation, it is controlled by K minus 1. So these are the two constants that is actually regulating the breakdown of this complex formation. So K minus 1 and K2 has to be present over there. And as it is speaking of the ES breakdown, so the starting material is your ES. So let us see what do we have over here. So K minus 1 and K2 is in only one of the following options. So A is the correct option. Very good. Okay, so A is the right answer because K minus 1 and K2 are the two regulating factors that is regulating the breaking or the breakdown of the enzyme substrate complex. Okay, I think that is clear. Then we move on to the next problem. In a mixed inhibition, the enzyme inhibitor complex EI has a dash affinity for dash compared to that of dash. So what are the three fill in the blanks? So we have just moved from the breakdown of enzyme substrate to a question to from that we get from inhibitors. So here we are speaking of mixed inhibitors. So what would be the fill in the blanks? So what is actually happening over here? So previously we spoke about the enzyme substrate complex. Here we are looking into the enzyme inhibitor complex. So what are the options? Let us look into the options. When we cannot answer after looking into the question, we have to try answering after looking into the four options or the four hints that are given to us. So in the first place, it can be lower or higher. In the second place, it can be enzyme or substrate, and in the third place, it can be enzyme or substrate. Okay. Now let's try answering one of them. So actually, two of the options can be right over here, because if something has lower affinity than enzyme compared to substrate, the other will have higher affinity for the substrate compared to the enzyme. So now, can you try answering it? So let us see from let us in the second place, it can be either enzyme or substrate, that does not matter. But what is more important is that whether EI, that is the enzyme inhibitor complex, has higher or lower affinity for the substrate. Let us look from the perspective of the substrate. So if we go back to the slide where I was teaching about the mixed inhibition, there if we look that any enzyme inhibitor complex would be having a lower affinity for the substrate, because your enzyme inhibitor, the inhibitor is actually binding to your enzyme. So the affinity of the inhibitor to your enzyme would be definitely be higher. So the inhibitor would be having higher affinity towards your enzyme than your substrate. So if we see if there is an option, so higher for the enzyme compared to the substrate. So D is correct because it is having higher affinity for the enzyme compared to your substrate, and lower affinity for the substrate compared to your enzyme. So C and D both are the correct options over here. And if it is an MCQ kind of a question, you can answer either C or D, and both of them are correct. Okay, so moving on to the next one. Okay, this is a question from the Michaelis-Menten equation. So derivation from Michaelis-Menten kinetics occurs when there are multiple substrates, substrate binding is reversible, K2 equals to Kcat, and the enzyme displays cooperativity. So which of the following thing or things occur during the derivation of Michaelis-Menten kinetics? Okay, so let us see from the first one. So what does it say? So the let us see the options. There are multiple substrates. Substrate binding is irreversible. That is correct. Okay. The next one says the enzyme displays cooperativity. That is also correct. But K2 is not equal to your K-cat. That is not what we have derived from the Michaelis-Menten kinetics. So option 3 is incorrect. And so is there any 2 and 4? So if not, then there can be multiple substrate as well, because as there can, because why k2 not equals to k cat, what does that imply? That there can be multiple catalytic steps and there can be multiple substrates as well. So therefore 1 2 and the 4 would be the correct option. The derivation of Michaelis-Menten kinetics does not give any idea or information about the k2 being equal to k cat. So k2 not equals to k cat is what we can tell. So option C is the correct answer. Very good. Okay. Now coming to incompetitive inhibition. So in competitive inhibition, what is happening? An inhibitor binds to an enzyme at a site other than the active site only to the substrate, reversibly at the active site, covalently to the ES complex. So where is your inhibitor binding in a competitive inhibition? Okay, I have got one answer. Others, what do you tell? I've got an answer C. So what is a competitive inhibition? There is a competition that is going on between the substrate and the inhibitor. That much we need to keep in mind. So what are the options telling? The inhibitor binds to an enzyme at a site other than the active site. That is not correct. That is incorrect. Only to the substrate. Okay, it is going and binding only to the substrate. That is also not correct, because it is going and binding to the enzyme reversibly at the active site and covalently to the ES complex. No, it is going and binding reversibly at the active site but not to the complex, because there is a competition that is going on between the inhibitor and the substrate. So it can bind reversibly at the active site. So first the inhibitor might go and bind, and then when there is an increasing substrate concentration, the inhibitor might get freed off and the substrate goes and binds to the particular enzyme. So option C is the correct answer. Very good. Next one. Here we are seeing a particular figure. And the question is, what kind of inhibition is depicted in the particular diagram? So what kind of inhibition are we observing over here? So what do we see over here? So we have the enzyme, we have the substrate, we have the enzyme substrate complex. Okay, and then we have the inhibitor that you can bind to your enzyme as well as your enzyme substrate. Okay. Okay, so someone has said D, someone has said C. So what do we see over here? Let's go and check it out. So we have the enzyme, we have the enzyme substrate, and we have the two inhibitors. So it can go and bind to your enzyme as well as your enzyme substrate. What do we see over here? So it can only go and bind to your complex. Okay, so from there what can you tell which one is correct? Actually both C and D can be correct, because when there is no competition, then your inhibitor can bind to the enzyme as well as your enzyme substrate, as well as when it is a mixed type of an inhibition that is going on, your enzyme can your inhibitor can go and bind to the enzyme as well as your enzyme substrate complex. Now there is a trick. When there is a mixed inhibition, the alpha values will differ. But when there is a non-competitive inhibition, the alpha value remains the same. So depending on that, you can tell whether it is a non-competitive inhibition or a mixed inhibition. As of now, from this particular diagram, it's very difficult to tell whether it is going to be a mixed inhibition or a non-competitive inhibition. So I can tell that both C and D can be the correct answer. The next question, which of the following is not true for an isozyme? So what are isozymes? So basically isozymes are your enzymes, that particular enzymes that basically differ in your amino acid sequence, but they are catalyzing the same chemical reaction. Okay, so if I tell you this particular definition, can you give me an answer for this particular question? That isoenzymes are differing in only the structure of the amino acids or its buildup. Okay, but they are catalyzing the same chemical reaction. Okay, I've got an answer. Quick answers. Good. Okay, anyone else would like to answer? So if we talk about isozymes, they are catalyzing the same reaction, but no information I have said you about the regulation or the rate in which they are actually operating or catalyzing. So these isoenzymes have different, you can say, kinetic parameters, and they regulate differently. So what are they actually used for is that they permit the fine tuning of metabolism to meet the particular needs of, say, a particular developmental stage or a particular tissue and all. So just because they regulate differently, so therefore they would be having the different km values. So the option that is they have the same km values is the incorrect option. Okay, so not true. So they do not have the same km values. Their km values differ. So B is the correct option. Okay, the next question. When a product accumulates in a cell beyond an optional amount, okay, its production is decreased by inhibition of an enzyme involved in its synthesis. After the product has been utilized or broken down and its concentration is decreased, the inhibition is relaxed and the formation of the product resumes. This type of mechanism by which the concentration of certain cell constituents is limited, what type of inhibition do we observe over here? So when you see that you have enough amount of a product, the the inhibitor goes and binds and the mechanism stops. But when again the concentration reduces, the inhibitor just moves out, and again the substrate concentration is refilled. Okay, so D is the correct answer. It's known as the feedback mechanism or the feedback inhibition mechanism, right? Because that is when you are getting a signal from the body, that is now you have enough amount of the substrate or say the product, so you do not need the product anymore. So an inhibitor goes and binds, and again there is a signal from the body that now I need that particular product, like you see for glucose and all. So then when you getting a signal, then the inhibitor just moves and the substrate goes and binds and the product formation just takes place. So that is known as the feedback inhibition. So feedback inhibition is the correct option, option D. Okay, the next one. In Michaelis-Menten kinetics, Km is defined as. This is an easy question. You all can answer it. What is Km? Everyone should answer this. This is a direct question. So how do you define Km? I have got one answer. That is C. Anyone else giving me a different answer? Or everyone is happy with that particular answer? So what are the options over here? Concentration of substrate required to reach maximal velocity. Concentration of enzyme required to reach maximal velocity. Concentration of substrate required to reach half of the maximal velocity. Concentration of the enzyme required to reach half of the maximal velocity. So if we see the graph, what do we have? So here we have the substrate concentration, and here we have is the V naught, so maximal velocity. And then we have a graph over like this. So what happens? At half we have Km. So C is the right answer. Very good. So the concentration of the substrate in which you can reach half of the maximal velocity at that point is what you get as the Km. Okay, very good. Those who have given it correctly. Okay. The next one. The advantage of using Lineweaver-Burke plot is. What is the advantage of using this particular double reciprocal plot or the Lineweaver-Burke plot? And this is an MSQ question, so more than one option may be correct. So try answering it. Okay, you say all of them are correct. Okay, let us see what others are telling. No answer from anyone else? Okay. So what is the advantage of using a Lineweaver-Burke plot? So if we see that, the first thing that comes to our mind is that this is a rectangular hyperbola, and deriving an equation from this deriving an equation from this becomes very difficult. So Lineweaver-Burke plot helps in linearizing the Michaelis-Menten equation. That is correct. It is easier to extrapolate a straight line. That is also the same, so that is also correct. You get a straight line. The next two options which says the errors in Km and Vmax are small. The Lineweaver-Burke plot gives us no information about the error or the values of the Km and Vmax. We only know that whether it increases or decreases. But whether we can consider that as an error or whether that is accurate and precise, we get no such information about that. So as of now, we cannot tell whether the error in Kmax or Vmax is small or large because we have no information about that. And from the intercepts, we get two important parameters, that is Vmax and the Km. So A, B, D is only correct. C is the incorrect option over here. The next one. Which among the following statement is or are true? Let us see. So the statements are given. Acetylcholinesterase hydrolyzes the neurotransmitter acetylcholine in the synapses and terminates its activity and acts as the non-competitive and irreversible inhibitor. Due to pyruvate kinase deficiency, hemolytic anemia is observed. Both M-type and L-type isozymes of pyruvate kinase are allosterically regulated. There are two lyse residues and one histidine residue in the active site of the ribonuclease A or RNase A. So which of the options are correct? Although I have not spoken about these enzymes, but you must have studied about the structure of these enzymes and the function of these particular enzymes sometime. So just a small hint I can give you over here that if you know about the structure of a particular enzyme only, you can tell which of the option is correct or incorrect, because the other three would be correct. So that is the other three or two might be correct. Okay, let us see what is the first one telling. So acetylcholine esterase hydrolyzes the neurotransmitter acetylcholine. That is right. In the synapses and terminates its activity and acts as the non-competitive and irreversible inhibitor. So this is the correct option because we know about the function of the acetylcholine esterase. So let us see in which options do we have. So we have 1 and over here. So in one way, so B and C are not correct because 1 is correct. So we can eliminate the options. So when you do not know a particular answer, try answering like this. So you know 1 is correct. Now we have 2, 3 or 2, 3 and 4. So let us now see the fourth option. There are 2 lysine residues and 1 histidine residue in the active site of RNase A. That is incorrect because we have 1 lysine residue and 2 histidine residues in the active site of ribonuclease. So ultimately this is wrong and the correct answer is A. 1, 2 and 3. Okay, so 1 correct, 2 correct and 3 is correct. Okay. Now coming to the last set of questions. Let us move one by one. For competitive inhibition, the maximum velocity that can be obtained at increased enzyme concentration, increased substrate concentration, lower substrate concentration, half of enzyme concentration. So for a competitive inhibition, when can the maximum velocity be obtained? Okay. Okay, let us see what others are telling. B. Okay, you have answered after a long time. Good. Try answering, even if you are not being able to catch up with the question. Try getting from the uh, MCQs what are the answers given over there, because these answers also tell you about what answer can be the correct one. Okay, so the more you try answering in the class, that becomes easy for you to answer in the exam, because then you can get your concepts cleared. Okay, so what options did I get as answers? C and B. Okay, so mostly yes, that is the correct approach from the perspective of the substrate concentration. Now, whether the maximal velocity should be obtained at lower or higher substrate concentration. So when we see that when we are increasing the concentration of the substrate, what is happening over here is that it's in competitive inhibition. So the inhibitor have equal probability of going and attaching to the enzyme or binding to the enzyme active site as equal to the substrate. So the more substrate concentration will actually stop the inhibitor from binding to the active site. So an increased substrate concentration will help you to get the maximum velocity. So for a competitive inhibition, the maximum velocity can be obtained when you are actually increasing the substrate concentration, because at that particular stage your when more amount of substrate is present, the substrate will go and bind to the enzyme, and you can obtain the maximum velocity at a faster manner. So B is the correct option over for this question. The next one, with increase in the inhibitor, with increase in the concentration of the inhibitor, the Km value increases in case of. So in which case do you observe the Km value to increase? For which case of inhibition? Try recollecting from the last table that I showed you. For which case the Vmax is same, for which case the Km is changing, for that. So in which case does the Km value increase? In what type of an inhibition? In only one case you would be seeing the Km value to be showing an increase. Competitive inhibition. Okay, let's see what others tell. Yes, that is the correct option. Competitive inhibition, the Vmax is the same and your Km value is increasing, because that is alpha Km. Very good. The next one. In the Lineweaver-Burks plot, the y-intercept gives you what value? Very easy question. So what are you getting from the y-intercept? B. Okay. Anyone else answering? B. Yes, so 1 by Vmax is what you get in the y-intercept, and for the x-intercept is minus 1 by Km. But for this one, we are speaking of the y-intercept, so 1 by Vmax is the correct option. Very good. The last question for today. During non-competitive inhibition, the inhibitor binds to a site which is called as the what site? Active site, allosteric site, inhibition site, or the binding site? You are saying allosteric site. Okay. Any other answer? So B and C. So there is a confusion between B and C. Okay. As of if we consider from the perspective of an enzyme, the mostly commonly sites that we have heard of is the binding site, or that is what we call as the, okay, so we have heard of the catalytic site and the active site. There is another site that is called the allosteric site. So what is the role of this allosteric site? So this allosteric site is responsible, that is actually regulating the enzyme's biological function. That is whether the enzyme should be turned on to give you the product or should be turned off to means whether to stop the product formation. So your inhibitor, if your inhibitor is going and binding to the allosteric site, if it is going and binding to the active site, the substrate, it is a totally a stop process for the formation of your product. So that is total stoppage of the product formation. But if it is going and binding to a site that is other than the active site, then that is the allosteric site. So what is the role of this particular site? So when you're inhibited, it is same as that for the feedback inhibition that I spoke. So when you do not need a product, the inhibitor is going and binding and stopping the enzyme from forming the product. But when you do not when you need the product in excess amount, then the inhibitor just moves out or just falls off, and the product formation becomes easier. That is, the enzyme and the substrate can form the complex and give you the particular product. So during non-competitive inhibition, the inhibitor binds to the allosteric site, and it is responsible for regulating the normal function of your enzyme, for the switching function of the enzyme. So that is, the correct answer is B, and that is the allosteric site. Okay, so that's all from my portion. Okay, so if you have any questions, you can ask me, else I think we can end the class. Okay then, so no other questions. Okay, thank you all. See you in the next week with a different lecture. Okay, have a good day.